Hi everyone, in this video we will discuss regression, both simple regression and multiple regression, and we will look at a few examples of how to do it in Minitab. As always, I like to start by providing a definition, some conceptual understanding, and then the null and alternative hypothesis. So what is regression? It is a statistical method that models the relationship between a continuous response, that is y, and one or more predictors, usually denoted as x. Let's explore what each of these terms mean. So the first thing to understand is that regression requires a continuous response variable, right? Regression can be done with categorical variables as well, and that's called binary logistic regression. In this video, however, we are focusing on using continuous response variables. So continuous data is anything that can be measured on a scale or a continuum. So things like weight, temperature, cost, and AHT, which will be our example, is continuous response. If you have categorical data, then we could use logistic regression instead, but we are not doing that in this video. The second thing to understand is a predictor. So in simple regression, you have only one predictor, an x value to predict y. So say you want to predict sales using advertising expenditure, you would use simple regression. If you want to predict sales using advertising expenditure and salesperson tenure, now you have a multiple regression model because you have two predictor inputs, right? And as we will see later in our example, adding more predictors doesn't necessarily improve the model. The next thing to understand is the term relationship here. What does that mean? So what regression basically does is it fits it fits a line through your data. It's called the best fit line. So the regression equation itself is in the format y equals b0 plus b1 x1 plus b2 x2 and so on, plus the epsilon. That epsilon is the error term. That's the gap between what the model predicts and what actually happens, right? But I want to understand what I want to explain what the line of best fit means. So let's say you have you plot your data in this format in a scatter plot. You could actually plot multiple lines through it. You could draw line 1, you could draw line 2, you could draw line 3. But visually, it's not always easy to determine where the best fit line is. What Minitab and what all the other statistical packages, what they do is they calculate the best fit line using the least squares method, and that's the method that minimizes the square distance between the line and all the data points that you're seeing plotted here. So the line that minimizes the distance, that's the best fit line, and regression basically uses that line to come up with a model, right? All of this will become really clear when we are actually doing the analysis. So stay with me for just a few more minutes before we actually jump into Minitab. So now let's understand what the what's what of the regression equation. So y is as I mentioned, it's the response variable. It's what you're trying to predict. B0 is basically the y-intercept. It's what happens to the response if you set everything else to every other value to 0, all the predictors to 0, then that's your y-intercept. B1 and B2 are the slopes, so they indicate how much y changes when one unit increase or one unit change is made. It could be increase or decrease as well, right? X1 and X2 are the predictors. So and the epsilon here is what is the residual. So that's again the gap between what the model predicts and what actually happened. So as I said, all of these will become clear and come to life when we start analyzing the data. Let's quickly look at the null hypothesis and the alternative hypothesis for regression. The null hypothesis is that there is no linear relationship between x and y. In other words, the slope or p1 is equal to 0. The alternative, of course, is that there is a linear relationship, so which means that the slope is not equal to 0. There are, in addition to the p-value relating to the hypothesis, there are some other stats that help us evaluate how good a regression model is. The, the, the most important among them is R square, which is basically the percentage of the variation that is explained by the model. P-value, again, it just shows whether a relationship is statistically significant or not. Variance inflation factor, very important, and we'll spend quite some time actually doing this. What this determines is whether predictors are correlated with each other. The benchmark industry, generally speaking, the industry benchmark is that if the VIF is more than 5, that's a red flag. That shows multicollinearity. And again, if that term is not familiar to you, believe me, we will discuss it in great detail. Then there are residual plots. So Minitab generates residual plots. What the residual plots, what they show is our model, the assumptions underlying our model, do they hold? Is there sufficient normality in the residuals? Is there constant variance and independence using the versus fits and versus order graphs? So those are some of the other stats that we need to look at. Now let's look at the example that we're going to use. So the example we're going to use is this. A call center wants to understand what drives AHT, right? And initially we will look at up to 4 predictors: agent experience, training hours, utilization percent, and calls per shift. And then later we'll add a 5th one to see how VIF changes when we add the wrong kind of predictor. What do I mean by the wrong kind of predictor? So we know that AHT includes after call work, right? So here is the standard formula for AHT. It includes talk time, hold time, and ACW. What we are going to do in our analysis is we will first run it without ACW, and then we will run it, we'll treat ACW as a separate component, and we'll try to use it as a predictor. That's what will lead to a spike in our VIF, and that's what we call the multicollinearity trap. So basically, if you use something that is correlated with other predictors, you will have a bad model, and I will show you how bad it looks and how VIF changes when you add a predictor that is not useful. Now let's quickly look at our data. So here is the data. We have data for 50 agents. We have their average AHT in seconds. We have their experience in months. We have the number of hours of training they've attended. We also have their utilization percent. We have the number of calls they've taken per shift, and we have ACW, which we'll use later. Now let's first start by simply copying and pasting our data in Minitab. So here it is. I'll go ahead and paste the data. So first, let's do a simple regression and predict AHT by using only experience in months. To do that, you need to go to Stat, Regression, and Fitted Line Plot. So you see, when you click on fitted line plot, and later I'll show you the other option there, it opens up this dialog box which has only one predictor. So in this case, you will use only one predictor. So our response is AHT in seconds. The predictor is going to be experience in months. The type of regression we are doing is linear regression. In all these other options, the one thing you want to check is go to graphs, and instead of these individual plots, you want a 4-in-1, and you'll see why in just a minute. It actually makes it very easy to view everything in a consolidated graph. So that's it. Hit OK, and Minitab is going to generate the output for you. Okay, we have our output here. Let's zoom this a little bit so you can see it clearly. Now, Minitab says that the regression equation is 528.7 minus 1.479 times the experience month. So what this basically means is that for every extra month on the job, an agent's AHT reduces by about 1.479, or roughly by about 1.5 seconds. So the more time you spend, the lower AHT you have. So in regression terms, the way to think of it is that in an additional unit of increase in months will reduce the AHT by 1.5 seconds. The next thing to look at is model summary. And I mentioned that we will look at R square, and that let's look at that. So the R square is about 37.09%. What that means is that this predictor experience in months, it explains about 37% of what drives handle time. So it's very meaningful. 37% of something is huge, but there's more to the story, and we will rerun this analysis with all these other predictors as well. But before that, let's also look at this analysis of variance. What we are looking at here is the p-value for regression, which is effectively 0. So it is less than 0.05. Recall that the null hypothesis was that there is no linear relationship between x and y. Well, our model is telling us otherwise. So it says that there is a relationship. And when you scroll down further, I'm just going to zoom a little bit so you can see the graph. When you scroll down further, you can see the downward trend clearly. So what's happening here is that agents who have more experience in terms of number of months tend to have lower HT. On this left side, agents who have, say, only 10 months of experience tend to have high HT. They're newbies. They're still learning their job, right? So lastly, let's look at the residual plots, and this is why I had checked that 4-in-1 option in graphs. So looking at like all four of them, they look pretty boring, and that's what we want. By boring, what I mean is we don't want to see anything extraordinary or unusual. No patterns, no funnels, no curves, right? Our model assumptions, they seem to be holding up nicely here. More or less, you can see that the plotted values are very close to that red line, so they're roughly normal. In versus fits, you can see that this resembles a random scatter. This histogram here is roughly bell shaped, and in versus order as well, you see it's pretty independent. There's nothing unusual about it. So overall takeaway for this first simple regression is that experience in months is a significant predictor of AHT. Now let's go ahead and add a few more predictors and do a multiple regression. So to do a multiple regression, you need to go to stat again, a regression, and this time you need to go to this regression menu and choose this one, the one that says fit regression model. So when you click that, this dialog box will open up. In responses, what you want again is AHT in seconds. In continuous predictor, you want experience in months, training hours, utilization percentage, and calls per shift. We will leave ACW seconds for now, but we will come back to it. Categorical predictors are gonna be blank. Under graphs, go back again and check that 4-in-1. It makes it very easy. Now there's a bunch of other stuff in there that we don't really need for our purposes. So for example, if you look at something like validation, it's got this option for k-fold and validation with the test set. We don't really need it for our purposes. Similarly, something like coding is used for categorical predictors. We don't have any categorical predictors. And the other things as well, we can just leave as blank. And if you click OK, this time around, we have a more comprehensive report. So let's zoom just a little bit. So as I said, the report is more comprehensive. It's got more predictors. So let's first and foremost, let's look at the regression equation. So here, what what the model is saying is that this is about 1.25. Yeah. So experience in months reduces AHT by about 1.25 seconds. Training hours, like the more training you attend, each additional hour of training can reduce the AHT by 1 second. Interestingly, utilization, that is if you know your agents are overworked, that can add 2 seconds to the AHT, so that's not good. And then you have calls per shift, which has a very small number here, that's 0.02 seconds, right? But but the way to interpret this is alongside the coefficients table. So let's look at the coefficients table, right? It's got a lot of stuff. So it's got coefficient here, which refers to the direction and size of each effect. And then it's got standard error of coefficient, which tells you how precise that estimate is. But for us Lean Six Sigma practitioners, I'm assuming that's who most of you watching this video are. For us, the main thing to look at in this table is the p-value and the VIF. So when you look at the p-value, all the p-values are 0. So except for calls per shift. So what our p-values are telling us is that experience in month, training hours, and utilization are all statistically significant. Calls per shift, as I mentioned here, it's the impact is minimal, and that's what the p-value is also showing, that it is not significant. The p-value is greater than 0.05 here. For all the VIFs here, the various inflation factors, these are all around 1, so which is very good. Don't forget these numbers, because in just about 2 minutes these are about to get changed, right? Now let's scroll down and look at our model summary. What's our overall model summary? So our overall model summary now shows an R-square of 95.49%. That's a massive jump. Just to compare, when we were doing just simple regression using one predictor, R-square was only 37.09%. Now it has increased to 95.49%. But what R-square basically does is it tends to increase when you add variables, even useless ones. So the better thing to look at is R-square adjusted, which is almost the same as R-square, which is a good sign. If R-square drops when you add a variable, then it just means that variable is not adding value, it's not worth keeping. So all in all, like, you see how the predictive power has increased from something like 37 and 35% to almost 95%. And R-square predicted basically just means that how well the model can predict new data that it hasn't seen before, right? The S here, this is also important. The S here stands for the standard error of the regression. So an S of 10.7334, let's just say roughly 11, what it means is that predictions are typically, plus minus 11 seconds. So let's say if an agent's AHT is predicted to be about 480 seconds, so that's roughly 8 minutes. So the model is saying that agent will have a plus minus 11 second gap in that prediction. Now, analysis of variance. Now, I did not discuss it in the simple regression, but it's worth addressing it now. If you're wondering why is there an ANOVA analysis in regression, right? So, well, what ANOVA as a technique, what it's doing here is it's breaking down where the variation in AHT comes from. So, right, and again, it's got a lot of stuff in here. It's got degrees of freedom, adjusted sum of squares, mean square, and whatnot. It's got the F value, but again, as Lean Six Sigma practitioners, we are gonna focus on the p values, and the result is the same as in the coefficients table above. Effectively, we it's confirming the same thing, that experience in months, training hours, and utilization are significant drivers of AHT. Calls per shift is not so much. Then there is another output here that's called fits and diagnostics for unusual observations. So what this is highlighting is that observation number 28 has something unusual, right? So observation number 28 means that if we scroll down here, that's the agent that we coded as agent 028. So for this particular agent, the residual is pretty large. So nothing alarming, but it's something worth investigating. Now again, the basically, if we look at the residual plots and everything again, we see that the residuals are actually even better this time around, even more closely approximating the covering the red line. So if you want to do a thick pencil test that ASQ calls, this is normal. The versus fits shows random scatter. This histogram is reasonably bell-shaped, and this versus order doesn't show that there's anything extraordinary. Now, as promised, let's rerun this analysis, and this time around we will add ACW and see how some of these numbers change. So the shortcut to, if you want to open the dialog box again in Minitab, is Control E. So let's just hit Control E and this opens. So it's already pre-selected what was already selected. The only difference this time around is going to be that I'll click here and I will add ACW seconds, right? So ACW seconds is added. All the other things are selected as. I just want to confirm. Yep. So 4 in 1, and we hit OK. Now look at what happened, right? So let's zoom. Let's go straight to let's go straight to VIF here. You see, compared to this previous table where all the VIFs were for experience month, training hours, and so on were around 1, now adding ACW has not only ACW's VIF is very high, it has inflated other VIFs as well, right? So all in all, adding ACW, which is already a part of AHT, is actually contaminating our model, right? So ACW itself is kind of, it's basically useless in this case, and we shouldn't retain it in our model. So again, looking at the coefficients as well of specifically of ACW, minus 0.184, it's completely insignificant. That's what the p-value also shows. It's greater than 0.05. If you look at the model summary, the R square is 95.49, which is what it was here as well. So that's essentially unchanged. The R square adjusted is 94.98, slight drop from 95.09, and the R square predicted has also dropped just a tiny bit. So why did this happen actually? So what has happened is that ACW, because I showed earlier that ACW is included in AHT. If we take this apart and try to use this separately as a predictor, our model suffers. We get inflated VIFs, our model summary doesn't increase at all. So all in all, we add a predictor that doesn't add any value, right? So basically what Minitab is telling us through this inflated VIF is that this variable is redundant. It's sharing information that is being captured by all these other predictors, so we can remove this from our analysis. So basically the good or the useful analysis that we did was the second one, which excluded which did not include rather ACW. It included only experience in month, training hours, utilization percentage, and calls per shift. So all in all, like on the basis of all of this, like what should the management do, right? If ultimately you're doing this analysis so you can make data-driven decisions, right? So firstly, drop ACW and calls per shift. These are not significant. ACW was not significant. It messed up the entire model. You can remove calls per shift from the model as well because it's statistically insignificant. The highest driver really is experience in month. So the management of the call center should actually invest in basically retention, in retaining agents, ensuring that they stick around long enough so they can gain experience and they can have good metrics. The second thing is upskilling through training, right? It shows that the model shows that for each hour of training, the AHT is reduced by 1 second. That makes sense. The more skilled you are, the faster you'll be able to handle your work. And utilization, this is also important. Utilization, it simply means don't overload agent, because every 1% increase in utilization is actually adding about 2 seconds to the AHT. So across, if you extrapolate this analysis across thousands of calls, over the month, then these seconds here will add up and they will amount to real headcount and costs, like, real headcount reduction and cost savings. So that is why regression is such a powerful tool. It tells you where exactly to focus, also where not to focus. All in all, this has been a long video. I hope you found this useful. Thank you for watching.